Hello students, welcome to the course on Basic Electronics Engineering and the course code is EC101. This is the course for BTech first semester CSC, IT and FT students and second semester EC students. Myself, Dr. Shurajit Bosak, Assistant Professor of EC Department, Guru Nanak Institute of Technology, Kolkata. And this is my official email address. In the last class, we have discussed on PN junction diode with applied bias. And we have studied the energy band diagram of forward bias as well as reverse bias. And also we have studied the current voltage characteristics curve for forward as well as reverse bias. And we have also expressed the mathematical expression for current voltage expression and the temperature dependence for diode characteristics and IV characteristics curve of ideal diode also. Now today let us start lecture number 3 from the module 2, that is PN junction diode and its applications. And the topic for the today's discussion are PN junction breakdown. What are the conditions? What are the types of breakdown? That is avalanche breakdown and zener breakdown. Concept of junction capacitance, zener diode and its characteristics. And the lesson objective is study PN junction diode, ideal diode, diode models and its circuit analysis, application of diode and special diode. And this topic is mapped with CO number 1. So let us start lecture number 3 from the second module, that is PN junction diode and its applications, with the topic of breakdown. Breakdown phenomenon in PN junction. So this is the IV characteristics curve, as already we have studied for forward bias as well as reverse bias. Now see, when a PN junction is in reverse bias, then a small constant reverse saturation current due to thermally generated minority carriers flows through the diode. With increasing reverse bias, a stage is reached when the current increases very sharply without any increase of bias voltage. The reverse bias at which this phenomena occurs is known as breakdown voltage. Already we have discussed on. And the question is why this breakdown occurs. The reverse breakdown in a PN junction takes place due to two physical mechanisms called zener breakdown and other is avalanche breakdown. Zener breakdown occurs in heavily doped PN junction through tunneling process at low reverse voltage up to a few volt. An avalanche breakdown which occurs in almost all PN junctions through impact ionization and avalanche multiplication process at high reverse voltage up to thousands of volts. So normally avalanche breakdown occurs in PN junction diode and zener breakdown occurs in heavily doped zener diode. Now we are going to the detailed discussion of first zener diode, or better to the zener breakdown. Then we move for the discussion of avalanche breakdown. So first is the zener breakdown. Zener breakdown basically occurs in zener diode, and the symbol of the zener diode is like that. Its upper is like a Z, cathode side, a Z side. That is the difference between a normal PN junction diode and zener diode. So zener breakdown occurs in heavily doped reverse biased PN junction diode due to a process which is called quantum mechanical process, or it is called band-to-band tunneling. In fairly highly doped reverse bias PN junction, the energy bands are crossed at low bias voltage. That is, inside conduction band H is lowered with respect to P side valence band H. The peak electric field at the junction approaches values of the order of 10 to the power 8 volt per meter in silicon. Such a high electric field is possible if the junction is abrupt and doping concentration on both P and N region are high, so that the depletion layer width becomes narrow. Electrons may tunnel directly from occupied or filled states in the valence band of the p-type material into empty or unoccupied states of the conduction band of n-type material through a narrow barrier of width, say W, separating the two bands. Tunneling, see, this is the tunneling phenomena which is shown here. See, so the tunneling of electrons from the field valence band of p-type material to the empty conduction band of n-type material gives rise to a reverse current from N to P. With the increase of reverse bias, the slope of the energy band in the depletion or space charge region will be steeper, and consequently barrier width will be narrower and tunneling current will increase. The fundamental condition is that a large number of bound electrons are available which occupy the energy states of the p-type valence band, separated from a large number of empty states of n-type conduction band by a narrow potential barrier of height equal to band gap energy. So the zener breakdown voltage due to tunneling for silicon and germanium PN junction is found to be less than say 4 Eg by E, where Eg is the say band gap uh, energy. So ultimately the zener breakdown mainly occurs, what is the conclusion part, that it is zener breakdown occurs in heavily doped reverse bias PN junction, and this process is called quantum mechanical tunneling or band to band tunneling. Next is the avalanche breakdown. Avalanche breakdown occurs in lightly doped reverse bias PN junction, not highly. Lightly doped reverse bias PN junction. And this breakdown is due to impact ionization and avalanche multiplication of charge carrier at a high reverse voltage and high electric field at the junction. So the process is called impact ionization and avalanche multiplication of charge carriers. So what does it mean? See, an electron or hole entering from the p region or n region respectively as minority carrier acquires sufficient energy in between collision due to high electric field existing at the junction. The electron or hole moving through the depletion region at high electric field gain sufficiently high energy to cause an ionization collision with bound valence electrons called impact ionization. Cause an ionization collision with bound valence electrons called impact ionization to generate electron hole pair. The initial electron moving with very high energy called say hot electron transfer its energy during impact with bound electron to bring the valence band electron into the conduction band, thus creating a electron hole pair. Thus the initial electron should have at least minimum energy consistent with energy and momentum conservation called threshold energy, which should be greater than the band gap energy to initiate a transition of an electron from valence band to conduction band in the impact ionization process. The generated electron and hole move in opposite directions, see here, in the electric field and may acquire sufficient energy to cause further impact ionization collision to create additional electron hole pair, initiating a chain reaction which leads to very high reverse current. Thus, the number of current carrying charges, that is electrons and holes, get multiplied, and this process is known as basically avalanche multiplication. This figure shows the impact ionization process, where a high energy conduction band electron in the initial state scatters from a valence band electron, generating one electron and one hole. In the final state, two electrons are available in the conduction band and one hole in the valence band. So this is actually the process is avalanche multiplication. One hot electron gets sufficient energy and it collision with other atom and create electron hole pair and impact ionization. That means it transfer its energy until they are equal. So, and then other free electrons again get sufficient energy and then it collide with other atoms. So this is a multiplicative process and ultimately large number of electron hole pairs are generated. So in this way, avalanche breakdown occurs or we get a huge amount of current after a certain amount of voltage, or it is called as a breakdown voltage. Next is the difference. It is a very important question. Difference between zener diode and avalanche breakdown. First is zener breakdown occurs in heavily doped reverse bias PN junction, so that the depletion layer is being narrow, but the avalanche breakdown occurs at junctions which are being lightly doped, so that it have a wide depletion layers. This breakdown voltage sets a very strong electric field across the narrow depletion layer. But here high electric field is not strong enough to produce zener breakdown. Now third point is, here the electric field is very strong to rupture the covalent bond, thereby generating electron hole pair. So even a small increase in reverse voltage is capable of producing large number of current carriers. But in avalanche breakdown, here minority carriers collide with semiconductor atoms in the depletion region, which breaks the covalent bonds and electron hole pairs are generated. Newly generated charge carriers are accelerated by the electric field, which results in more collision and generates avalanche of charge carriers. This results in avalanche breakdown. And the fourth point is, zener diode has a negative temperature coefficient. That means breakdown voltage decreases as temperature increases. But avalanche diode exhibits positive temperature coefficient. That means breakdown voltage increases with increase in temperature. Okay. Next is the junction capacitance. In the depletion region of a PN junction diode, immobile fixed positive charge of donors on N side and negative charge of acceptors on P side form a dipole layer. When the PN junction diode is reverse biased, The width of the depletion region increases with the increase of reverse bias voltage as majority carriers flow in or out of this layer. The depletion layer acts as a dielectric, that is non-conductive medium between P and N regions on either side of the junction. Therefore, these regions act as two plates of a capacitor separated by a dielectric, that is depletion layer. The capacitance of the capacitor formed in the junction area is called junction capacitance, depletion region capacitance, space charge capacitance, or transition region capacitance. This capacitance is similar to that of a parallel plate capacitor given by the expression C equal to epsilon A by D, where epsilon is the permittivity of the dielectric between the plates of area A and separated by a distance D. So the depletion layer is like a parallel plate capacitor. That is why it is called the junction capacitance. And the feature of the junction capacitance is widely see in a diode which is called basically varactor diode, which actually operates in a reverse bias PN junction diode basically. So varactor diode is a reverse bias PN junction diode whose junction capacitance can be varied with the applied reverse bias voltage in a controlled manner. See the junction capacitance. And varactor means basically variable reactor, and it is also known as varicap or variable capacitance. So the reverse bias curve junction capacitance with respect to the reverse bias voltage or VR, say it is like a parabola, and this is the symbol for a varactor diode. Just see here a parallel plate capacitor is present. So that's all about PN junction diode. And now I am going to solve a numerical problems. And this type of problem is normally comes in the semester exam. The problem is like that. The 6-volt zener shown in the circuit has 0 zener resistance and a knee current of 5 milliampere. Calculate the minimum value of R so that the voltage across the zener diode does not fall below 6 volt. See, the circuit is like that. Then what is the solution? Now so you have to find the resistance value, minimum value of resistance, so that the voltage across the zener diode does not fall below 6 volt. So the output voltage across the resistance R is regulated to 6 volt. Therefore, the current I. See, therefore, this current I is 10 minus 6 by 50. See, 50 is the resistance here. Resistance 50 ohm and 10 volt here 6 volt. So 10 minus 6 by 50, which is 80 milliampere, 0.08 ampere. And the knee current is 5 milliampere. So hence the load current I2 is 80 minus 5 equal to 75 milliampere. Therefore, the resistance R is the 6 volt 6 voltage by current. So 6 volt by 75 milliampere. So 75 into 10 to the power minus 3, which is 80 ohm. So the minimum resistance value is 80 ohm, so that the average voltage across the zener diode does not fall below 6 volt. Okay, so this type of problem normally comes in semester as well as gate type questions. So this is all about PN junction diode and breakdown voltage. In the next class, we discuss on the application of diodes. So thank you so much today. Now I am ending the session.